Okay, so part we're just going to revise through everything that we need in the conic sections. So ideally, when it comes to conics, there are, 4 conics that you have to keep in mind. So let's just quickly put them down so that you guys know what we're looking at. So we're going to have the first and most basic conic section is going to be a circle. Then we're going to have a parabola. And then we're going to look at an ellipse. And then I'm going to look at a hyperbola. So these are the 4 types of conic sections that we're going to review. And each one of them is going to have specific characteristics. So again, we're just having a quick review of each one of these conic sections. So when it comes to a circle, let's look at a circle very quickly. So when it comes to a circle, what do you need to keep in mind? A circle has 2 forms. If it is centered at the origin, meaning at 0, 0, then a circle will have a formula that looks like this. And then this will be equals to r squared. So sometimes they'll square root both sides so that you only have r on the right-hand side. So this is a circle centered at 0, 0. But if a circle is not centered at the origin, centered somewhere else, then you expect that this is going to have x minus h squared plus y minus k squared. And then the radius, of course, will still be just r squared. This is for a circle centered at h, k. Now, how do you determine a circle? How do you actually find an equation of a circle? Well, to determine an equation of a circle, generally, all you need are just at least 2 points. So you only need 2 points to predict an equation of a circle. Now, how do you actually do this? So we can have basic examples. Let's find one example. Sorry for that. So yeah, if you have 2 points, you can describe your circle. You can find its center, and if you know its center, then you can easily find its radius. So if you have 2 points, then one of them has to be at the center, meaning that's basically where the circle is. The circle is going to be centered. But if none of the points is located at the center, then to describe a circle, you actually need at least 3 points to be given. So to describe, of course, these conic sections, you must state its equation. And if it's a circle, then you must also state what its radius is. Now, let's try to look at just a few examples. So we have one example here. In this case, we have we want to find an equation of a circle whose center is at 2, 3. So this circle is centered at 2, 3, and it passes through a point 5, -1. So we have 1 point at the center, 1 point along the circumference of that circle. So how do we then find the equation? So if this is our circle here, and this is our point, this is given as 2, -3. So you have this is 2, -3. And then we're given another point, this is 5, -1. So you can place it anywhere really, it doesn't matter. So 5, -1, let me just get this. This is -3. Okay, just got that. Let's do this. So if this is our center, let's position our point 5, -3. We'll put -1, I mean. We'll place it somewhere here. Of course, I'm just putting it there randomly. Now, if this is where our 5, -1 is, to give the equation of a circle, how do we do that? Well, the radius can be found. We know to say, since this is obviously not centered at the origin, it implies that we are dealing with this version of a circle. So the left-hand side becomes quite obvious. For the left-hand side, it is x minus h, because since our center is here, it implies that our h is 2 and our k is 3 there. -3, I mean. So this is going to be -2 squared. Then we have plus y minus our k, and our k is -3 squared is equals to r squared. So this becomes x minus 2 plus this becomes y plus 3 squared. But how about that radius there? So we still have the radius to figure out. And to figure out what the radius is there, we are now going to go back and use those 2 points. The radius, if you look at this, since one of the points is at the center, the radius will just have to be the distance between the 2 points. It's the distance from the center to any point on the circumference. So since we know those 2 points, finding the radius becomes easy. We're just getting the distance between 2 points. So the radius then can be evaluated as r will be equal to the square root of, we can choose which one is our x1, it won't really matter. So I can take x1 to be here, y1 to be here, x2 to be here, y2 to be here, or vice versa it will be. So to get the distance here, we know how it goes. This is going to be x1 minus x2, or x2 minus x1, again, doesn't matter, let me just be uniform. x2 minus x1 squared plus y1, y2 minus y1. So how do we proceed? So our x2 is 5, our x1 is 2. So we have 5 minus 2. Of course, that is just 3. Plus, then we have y2 minus y1. Our y2 is -1 minus y1. So I have -1 minus y1. y1 is -3. So you see this is going to be +3. +3 minus 1, this is going to give us 2. So we get a 2 there. So we have 2 squared. So this becomes √9, 3 squared, plus 4. So this comes out as √13. So r, the radius, is equals to √13. Or we can say r squared is equals to 13. And remember, for our radius, this is what we have there. So where in place of r squared, we just put 13. So here we have 13. So here we have found the equation of that circle. Now, what we'll do is I'll ask you guys to try out the question as well and see if you can pull it off. Again, here, the question is find the equation of a circle which passes, or whose center. So for the question I want you guys to try, we have the center is at -2, 1, and it passes through a point 1, 3. So you guys can try this out later and let's see what you find. So this is how you describe a circle, and that is the standard expression for a circle. Next up, we have the parabola. Now, what is a parabola and how do we describe it? So we'll skip the definition of a parabola, and what we just look for here is exactly what we need. Some of the concepts will come out when you start describing what a parabola is, when you start looking at examples. Generally, a parabola, depending on what you're looking for or how it looks like, a parabola will have an expression of x squared is equals to 4yp. Now, what is p in this case? Well, in this case, this, for example, is going to be a parabola that opens upwards for once. You can tell that this parabola opens upwards because it must occur to you, or you must know this equation very well. So in an expression where you have y is equals to x squared, you know to say this equation opens upwards. So once you remember that this equation opens upwards, so when they switch to now place x squared as subject, and then maybe just add a coefficient there, it should not confuse you. You should still be able to recall that this expression opens upwards. So this is what we have here. But what is that p? What does it represent? And how do we actually deal with it? Well, p there is the distance from, let's create a simple sketch. Okay, p is going to be the distance from the vertex here to where the directrix is. So if the focus of this parabola is somewhere here, so we're going to give a vertical axis, something like this. And then we have this parabola is centered at the origin. It has the vertex at the origin. So we have something like this. So in this case, of course, this is our x-axis. And this is our y-axis. So here, P becomes the distance from this point, from here going upwards up to here, so that is P, and also from here going downwards up to where the directrix is. So that is going to be P. So in other words, the directrix will be located negative P below that parabola. So this is where the directrix is going to be. So if this is coming up to P, then you know this comes up to minus P. So basically this is our parabola. Now, by definition, you have to recall that a parabola is just a set of all points that are going to be equidistant. The distance from some point, which is the focus, coming up to the parabola. So this is a set of all those points. This distance has to be equal to the distance from here, coming downwards up to here. So this is how that definition of a parabola is obtained. So if we label that as, of course, I label that P as the magnitude there, but I can say if this is where the focus F is, and this is a point which is basically X, comma Y, and this somewhere here, remember I say this is at negative P. Here we have, this is at not P, this is at 0, comma P, and this is at 0, comma negative P. And this point here, obviously, will have to end up being at X, comma negative P. The distance, we can take this point as what? I can label this as maybe D. So you can now say the distance from F to P will have to be equal to the distance from P to D. So this is the expression we use to derive the definition of a parabola, because we're saying it's a set of all points which are equidistant from a fixed line, which we are calling the directrix, to a fixed point F, which we are calling the focus. Now, of course, our point F is the focus. So by reducing this, this is how we end up with the definition of a parabola. Now, that is for a parabola which is centered at the origin. So basically its vertex is at the origin at 0, 0. But what if it is not centered at the origin? If your parabola is not centered at the origin, then your equation changes. For y, it is going to shift by k. And then, of course, in this case, the one I started with was x squared. So let's start with x squared. So for x will shift by h. And then you had 4y. Y will shift also by k. And then we had p here. So this becomes the equation of a parabola which is not centered at the origin. Now, parabolas, of course, will come in different forms. This, for example, was for a parabola that opens upwards. Now, if a parabola opens either up or down, basically wrapping around the y-axis, then you expect it to be in this same form. X squared is equals to 4p py or yp. But if you see, or if we have a negative here or here, it doesn't really matter. But if we have a negative, then you know to say it's the same expression, but now it just opens downwards like this. So it's still wrapping around the y-axis, but now just opening downwards. Now, this is this format. But you can also have a parabola that opens to the sides, meaning wrapping around the x-axis. Now, if you have a parabola that opens to the sides, meaning you have one that either opens like this, or maybe that opens like this. Now, for such, how would they look like? Well, again, you have to be able to relate these parabolas to a graph of y is equals to root x. I hope you guys are able to make these relations, because I think y is equals to root x is something that you guys get to draw a lot. And if you get to draw that graph, usually it goes something like this. It only has positive solutions, of course, because the root cannot bring out a negative. So usually this goes something like that. But in this case, what we are looking at it from the part where this is squared, meaning you have to square this. So you end up with y squared is equals to x squared. So in this case, what you have is y being the term that is squared. And if y is the term that is being squared, how will it look like? Well, same thing, but now we're just looking at it from here. I want that. No, this one, not helpful. So it now implies that we have the same thing, but now it wraps around completely. Something like that. Now, if it is centered at the origin again, we're going to have something like this. Something like that. Now, in this case, again, now the focus is going to be somewhere here, and the directrix will have to be somewhere this side. So the distance again from here up to somewhere there will be the one that we're going to take as P. Of course, you know that distance will have to be the same as the distance from here to there. That will also have to be P. So if this is at 0, 0, then this will be negative P, and this is going to be at P, 0. Now, again, this is the where the directrix is, and that is the center, and that is going to be where the focus is. So this is going to be our parabola. But of course, the equation will not be as the way this one is. I just use this to give you an idea of how it will come out. What will be squared will be y, but now I have y is equals to 4px. Notice that it's the same equation we looked at earlier on, but it was just x squared is equals to 4py. So I don't say memorize everything that I'm going to put down here. I'm just saying just remember one or two, but find a way of relating those same ones to everything else. Once that is figured out, you should also be able to observe that if a negative were to be included so that you have this, then it would imply that it's still wrapping around the x-axis, but now it will just be something like this, but it will just open to the left. So of course, my curves are not really perfect, but you guys, I hope you get what I mean there. Okay, so same thing. If it's not centered at the origin, then you expect y minus k equals to minus 4p, and then x minus h. Okay, so with that done, any questions from this point before we start looking at some exam paper questions? Okay, let's look for some exam paper questions. Okay, so I found one question, but this question, it's not really about parabolas. So we'll come back and look at parabolas again, but this time around, look at the question that we have. So this is coming from the 2017, is it? Let me just confirm the year again. So this is coming from the 2017 test 1 for the School of Engineering. And we're going to use this question as our example. So if you do find that question, that is question 1A in that paper. Is it this? Yeah, this is actually test 2. So in this case, they're saying, find the center and radius of the sphere given. So we have a sphere, and this sphere is x squared plus y squared plus z squared minus 2x minus 2y minus 2z is equals to 1. So the question is asking us to find the center and radius of this sphere. So in our description, in our first description, we pointed out 4 conic sections, and the first one was a circle. You have to understand that a sphere is a circle, but in 3 dimensions. So a circle is in 2 dimensions, it only has x and y. So you have something like x squared plus y squared. But a sphere is going to be a circle, but in 3D, meaning it has that z component. So let's hope this doesn't get messy later on, because I haven't really gone through it. But let's see how it goes. So when you have a question like this, you're trying to get maybe identify, it can be a parabola, it can be literally any conic section, regardless of the number of dimensions. You're trying to understand its structure very well, figure out its radius or let's say directrix or something. The first thing that you have to do is complete the square. The best thing is you don't see a cross product. You see what the cross product is there, but it's not here in this case, meaning that we don't have to worry about rotating the axis. So here, of course, you have to complete the square. So arrange everything with an X together, everything with a Y together, and everything with a Z together. Where you keep that one to the left or to the right, it doesn't matter, but it will affect our calculation in one way. So I'll just bring it here. But even to the right, it can still be worked out. So for each part, I'll just group them the way I will be looking at them. I'll be looking at them in that way. So for each term, they make sure that the coefficient here is a 1, the coefficient of the 1 squared, the term squared. In this, x squared must have a coefficient 1, y squared 1, z squared 1, which is the case here. Once you have ensured that, next, focus on the term with an x, or the term with a y, the term with a z. Once you highlight those, half them. So I'll get x squared here. I'll write this term first the way it is, then I'll get half this coefficient. The coefficient there is -2, including the sign. I'll half it. So if I half that, I'll get -1. Then I'll square it. So I'll add it. That is -1 squared. I'll add it, then I'll subtract it. Same thing, -1. So all this becomes just this term here. I'll do the same thing for the others, but for now, let me show you how the first one will simplify. Everything else will simplify the same way. So when I simplify this, what happens is just these three here. You should know by now that just get the first term here, x, I'll just get x, and get the last term here, including the sign. So it's -1, and then square. If you try to expand this, it will give you everything here exactly the way it is. So this you should have seen. Oh, yes, it is. I just omitted that too. It is supposed to be squared. So these will reduce to this. When you square that last one there, it will give you -1. The negative in the brackets will die out. So seeing that if all these other terms have the same structure, when we use the same analysis on them, we expect to get the same conclusion. The first term, y -1, then squared, then -1. This is going to be what you will get from this one. And then when you do the same thing from the one with z, we expect to end up with z squared, not z squared, z -1 squared, then -1. Then you have that -1 outside there, not part of anything. So when you simplify this, now you have x -1 squared plus y first, y -1 squared, then plus z -1 squared. Then I have a -1 from here, -1 from here, -1 from here, and the -1 which is there. In the end, we have -4. -4 goes the other side, becomes +4. Now I'll ask you, what is the center of this sphere? What is the center here? What? 1,1. Yeah. 1,1,1. And the radius? The radius is 2. Don't be tempted to say 4. That is the radius squared. So the radius here is 2. So the question here was asking for the center of the sphere and the radius. We've seen that it was actually a very simple affair. Okay, let's try to find more questions this time around. Let's see if we can find something on the parabola. Have you guys found anything? Consider a case like this, where we have an equation like this. We just want to find where the focus is and also what the directrix of the parabola is. First and foremost, when you look at this, clearly this is centered at the origin. So we know where the center is. This is at the origin. When we identify the term that is squared, y is the one that is squared here. So this opens to the sides, either left or right. But because all the terms here are positive, so we know this will open to the right. So before doing anything, I can even sketch my parabola so that I have a visual representation of what I'm looking at. So the question does not ask for a sketch. You can provide it as part of your answer, or you can just do this on a rough paper so that it just is, so that it's just helpful to you as you work it out. So let's do this. Yes, this will work. So let's take that to be our parabola. Now, want to find, in the first part, find the focus. So that we know to say for such a parabola, the focus is located along the x-axis somewhere here. And then the directrix will have to be somewhere here. So the distance from the center here to the focus, that is what we need to find so that we understand where the focus is as our point F. Now, we know to say the standard expression is y squared is equals to 4px. But what we've been given in this case is y squared is equals to 10x. So you have y squared is equals to 10x. What does this imply? It implies that 4p, which is here, must be the same as whatever this 10 is. So 4p has to be equals to 10, or p has to be equals to 10 over 4, or 5 over 2, or 2.5. So we now know what p is. P is 2.5. What does that mean? It implies that the distance from here to here is 2.5, and the distance from here to here is 2.5. So you have, since this is a point, the focus, that's the point, we have to give it as x comma y. Along the x-axis, y is 0, so this becomes 2.5 comma 0. And this, on the other hand, is the location of the directrix, and we know the directrix will have to be a line like that. So to specify the directrix, we don't give a point. Instead, we give the equation of a line because that is a line. So the directrix will be given by, we can just state that, directrix. So here it will be x is equals to negative 2.5. So negative, because if this is positive 2.5, backwards has to be negative 2.5. So we're done with that. Now, what I want to just point out is that if we had the same example, let's say example 2. If we had the same example, but this time we had maybe y, maybe minus 3 squared is equals to, let's say, 10, and then let's say x minus 3. Notice that's the same example as earlier, but now the center has been shifted. So because this is not located at the center, what does it imply? Well, firstly, it's the same case, it's the same thing. The only difference is this is no longer located at the origin. How would we interpret it? I've picked the same question because we've already done the hard part. I just want to show you how you treat it if it's not at the center. So in this case, this is not located at the center. According to this, we know from y we get the value of k, from x here we get the value of h. And the location of the center will be h comma k. In this case, it will be 3 comma 3. I use 3 and 3. Okay, 3 and 3. Let's go with it. Okay, so how do we, okay, 3 and 3, that's okay. Okay, so how do we then play with this? So this is not at the center. We first find 3 comma 3. Let's say this is our 3, and let's say this is our 3, where this is our HME. So we have 3 here. So the center is somewhere here. 3,3. So it means that now our parabola still opens to the right, but it now just has to be at 3,3. Something like that. So once we have made sure that the vertex is at 3,3, now where will be the focus? So this, notice that this becomes the axis or the line of symmetry for our parabola. So it implies that the focus has to lie along this line. So the distance from here to here is P, and the distance from here going backwards is also P. Now, let's see, what is going to be our P? Well, it doesn't change the fact that what tells us what P is the coefficient coming from here, which is a 10. So we still have 4P being equals to 10. So we still have P is equals to 2.5. So in this case, our P is going to be 2.5 going this side. So let me not put it there. So 2.5, let's say our focus is somewhere here. But because we are already 3 units to the right, and moving from here coming up to here has to be 2.5. It now implies that the reading here will have to be 3 plus 2.5, which will now come out as 5.5. But also, this line is the line y is equals to 3. So the focus here now becomes a point 5,5 or 5.5, 5.5, 3. That becomes the position of the focus. The directrix, on the other hand, has to be 2.5 units, but now to the left. Since coming from here all the way up to the x-axis, the y-axis I mean, that's 3. So 2.5 means we don't reach the y-axis. Let's say we perhaps just come up to here. So the directrix has to be a line that passes through that. So where this is the line x is equals to, since the distance from here to here is 2.5, it implies that that's the line x is equals to 0.5. So this is how we would do it if this was not located at the origin. Any questions there?
Now, sir, how do we represent the ellipse?
The what? The directrix.
The directrix in that case.
The directrix is an equation. I think I already did. It's this one here.
No, sir. I mean, when the parabola is shifted to the other center.
Yeah, that's what I'm trying to show there. Look at this. This is what you have. And yes, this is shifted now. Let me shift it a little bit more so that perhaps it will be clear. Let me say this is shifted a little bit like that. So that I've changed it now. I've presented it like this. This is where the center is. Let's say this is at 3 and this is at -3. So the focus, if you move for the focus, if the distance you have to move, let's say up to here, is 2.5, it implies that on the x-axis, the reading here will be 5.5. But the directrix will have to be 2.5 backwards. So if you move 2.5 this side to the focus, then you have to move 2.5 back to find the directrix. So the 2.5 to the directrix will have to be there. What this implies is that the directrix will have to be passing along this line there. It will be a line that is 2.5 from the center there. But what is this line? So if you have to move 2.5 units back from 3, that is, so the directrix will have to be at a point where a 0.3 minus 2.5, which is equals to 0.5. So if you look at that, it gives you this point as 0.5. So you then conclude that the directrix will be the line x is equals to 0.5. Which is basically what I did here. I said this is the directrix. Do you get it?
Yes, sir.
Yeah.
Yes, sir.
Okay. So that is how we move with that. Any questions there? Okay, so you have this. What do you think? Is this something that you can manage to pull off? Will you manage trying out this question, or maybe we do this as well? Great. The ellipse. So again, the standard expression. Yes, please.
Can I just see the question?
Okay.
May you please slide a bit?
I do what?
Oh, that's the whole of it?
Yeah, write the equation. Write an equation for a parabola that opens to the left with the vertex 0,2 and passes through -6, -4. Hence, sketch the graph.
Okay, thank you.
My great. Now the ellipse. Now an ellipse has a basic format. If it is centered at the origin, an ellipse has got this expression, looks like this. Where this is equals to 1. So this is the standard expression for an ellipse that is centered at 0,0. Now, if it is not centered at the origin, just as you've seen so far, it will be x minus h over a squared plus y minus k over b squared is equals to 1. This is for an ellipse centered at h, k. Now, what is A here and what is B here? Now, the ellipse that we are describing with these formulas is going to be an ellipse which is more of a horizontal egg, if I would call it that. So we have the x-axis passing like that, and then we have the y-axis passing like that. So the idea here is that you have three letters. The first one is A. What is A? Well, A is the distance from the center of your ellipse to where the vertex is. So since I used A there, we can argue to say that this is at minus A and this is at positive A. The next important label or assignment is C. We are going to use 3 assignments, A, B, C. Now, C here is going to be the position of the focus. So if let's say the focus is, of course, we know to say an ellipse is going to have 2 of them, just like a hyperbola. So if one is here, let's say this is in the x-axis, this is meaning C is basically just the value of x. Here, C can be taken to be positive C. Y here is 0. While the other side, C can be taken as negative because we know the other side it's negative. So we have something like this. Someone trying to join us? Okay. Okay, so basically this becomes what our C is. Now, next up, these perhaps are the 2 main ones, but we can use these to actually predict what B is, and B is basically just going to tell us what that point is and what this point is. But these are the 2 main ones. Now, to figure out what B is, usually we just use A and C. So if you know A and C, you can find what B is. And if you know B and A, you can find what C is. Because we know to say B squared is equal to A squared minus C squared. So this is the connection between the three letters we're using here. Now, like I mentioned, C tells us about the focus. So C is saying stories about the focus. A talks about the vertex. So A is talking about the vertex. So these are the two key points about an ellipse. So if you know A, you can determine where the vertex is. If you know C, then you can describe where the focus is. But of course, you can't do either of these two if you don't know where the focus, where the center of the ellipse is. And the center of the ellipse is described by H and K. But usually we don't use H and K, but you just see by what you have being added or subtracted to X and Y. So with that in mind, let's see if we can find one or two examples to just help you guys get how you play with an ellipse. For the first example on an ellipse, we have something pretty minor. So for the first example, consider the case where you have, let's say, 16x squared, and then we have 25y squared is equals to 400. The first thing that you want is whatever you've been given, you want it to look like the standard expressions I gave earlier on. So in this case, you want to get rid of this 16 and 25. So what do? You want to divide by the lowest common factor, the lowest common multiple of these two terms. But in this case, you also want the right-hand side to end up being a 1, if this is an ellipse indeed. So to make the right-hand side a 1, you might as well just divide with that 400. So divide everything by 400. This side, 400 here, and 400 here. This will leave a 1 only. Here we have 16 over 400, x squared, plus 25 over 400 as well. And then y squared is equals to 1. Now we know to say 25 into 400, how many times does it go there? Is it 16 times?
Yes.
Great. So we end up with y squared over 16. Now we have 16 into 400. And here also, we see that we end up with 25. So this is the expression that we have. So now we can compare this with the equation for an ellipse. Now, how you distinguish, you know to say, if both terms are squared, then it's definitely not a parabola. A parabola only has either x squared, but the other one is not, or y squared and the other one is not. And the other side, you always have a 0, so that when the term which is not squared goes there, becomes the only thing there. But if both x and y are squared, then it's definitely not a parabola. It would be a circle, but for it to be a circle, then the terms in the denominator have to be the same. Or nothing, yeah, the terms in the denominator here have to be the same, either 1, 1, or 2, 2, or 4, 4. That's basically the condition for this to be a circle. But provided those are different, this is not a circle, it's not a parabola, meaning it's either an ellipse or a hyperbola. If both the x term and the y term are positive, then it implies that it is an ellipse. If either one of them, just want one here, if either one of them is negative, then you're dealing with the hyperbola. That is, if either term here is negative. Now in this case, both are positive. This is an ellipse. Now, what do we need here? The question here is to find the focus, the vertex, and hence create that sketch. Now, what you want to do here is to identify whether you're dealing with an ellipse that looks like this or an ellipse that looks like this. Now, the quickest way that you can use to identify this is this. You see, A is the distance from here to the center. And when you look at this, in the first part here, clearly A is going to be a very big number compared to B. B is going to be the distance from the center to that point. This is where B is. So A is bigger than B. But when you look at this part here, used to see A being bigger than B because now B is in the x-axis. What am I getting at here? When you look at your expression, if x squared is the one with a big number, 25, if you only write them as a squared, meaning this is 5 squared, but y has 4 squared, clearly the one with a big number controls how this ellipse looks like. If the ellipse lies or is horizontal, literally along the x-axis, it implies that the 5 is here. This is -5, and this is 5. And the B here is 4, which is smaller. It implies that basically this is where 4 is. So you have an ellipse whose measure is in the x-axis. But if you had something like x squared over, let's say, 3 squared, then plus you have y squared over, let's say, and even say 6 squared is equals to 1. Clearly here, the big number is associated with y. In other words, you have an ellipse whose measure is in the y-axis. So this is what you'd have here. And since A is 6 there, it would imply that from here up to there, this has to be 6. And from here coming down up to here, this has to be -6. So I hope you guys have seen that. The denominator, if y has a larger denominator than x, then it implies that the measure is in the y for this ellipse. And if x is the one with the larger denominator compared to y, then the measure is in the x. In our current example, x has a larger denominator. So our measure for this ellipse is in the x-axis. So this is what we're looking at. I've even started creating that sketch. We have already even identified where the vertices are. So we have -5. So basically, this is 25. We know you can write it as 5 squared. This is 16. You can write it as 4 squared. This identifies A as 5 and B as 4. So bringing our focus, our vertex to -5, since I said A tells the story about the vertex. So one is going to be at -5, the other one is going to be at 5. Next up, the focus, since we want the vertices and then the foci as well. So for the foci, where is it? You know, an ellipse will have 2. One will be here and one will be here. To get the focus, what we need is A and C. We know to say B squared is equals to A squared minus C squared. This implies that since we're looking for C, C tells us about the focus. C squared becomes equals to A squared minus B squared. A squared is what? A squared, we had 5 squared, which is 25. B squared, we had 16. So this becomes 9. So here we're seeing that C is equals to 3. So because C is 3, we now know to say we have to move from the origin or from the center 3 units to the right and 3 units to the left. So if we're giving them as points, the vertex, you can give it in 2 ways. In most cases, they like using for the vertex, since you know it is along the x-axis where y is 0. So you know it is at 5, 0. And the other one is at -5, 0. You can write it like this, but you find in most books, sometimes they'll just write 5 plus or minus, and then you have 0, or positive and -5, 0. This means the same as what we wrote earlier on. And then for the focus, or for the foci, again, it's also literally along the x-axis. So the y value there is 0. I'll use this shorthand. So we know it's 3 units to the right, 3 units to the left. So we have plus and -3, then 0. This tells us where the focus is. The next thing that they wanted us to do was to sketch. Guess what? This was our sketch, or this is our sketch. So if we have to, we can also show the y-axis. Okay, that completes our sketch. Okay, so I hope that part is okay. Now, the only thing I'd like to point out here is that if the ellipse was not centered at the origin, let's say you have an ellipse whose measure is in the vertical axis, something like this. Is this oriented? I think that. Is this better? We'll say yes. Let's say this is what we have. But let's argue to say that this ellipse is not centered at the origin. Clearly, first of all, the measure is along the y, but let's say this is not centered at the origin. Let's shift the center to something like here. Now, what happens in this case? Well, if let's say we know where the center is, so let's say this is at 3, and this is at, let's say, I can put -2. So if the center is at -2, 3, this could have been given to us in a number of ways. We could have had x minus, since this is minus there, this has to be plus squared. Then we have plus y minus 3 squared is equals to 1. Let's put our denominators there. I have put the measure to be in the vertical, so I want my y to have a larger denominator. So I'll put this to be 3 squared, and I'll put this to be 5 squared. So let's say this is our ellipse. Now, how do we play with this? Now, in this case, how it works, it's going to be like this. Of course, I hope this doesn't have an error, because I'm just basically just making up the question. Now, how do we work out this? Well, to find where the vertices are going to be, to say A controls where the vertices are. But which one is going to be A here? A is going to go where you have a larger denominator. When you're dealing with ellipse here, what takes A is going to be switching, whether it's this or that. So in this case, A is going to switch. It's going to be the larger one here. So A is going to go with the 5 there. So my A is going to be 5. What does that imply? It implies that from that center, my center is here. To reach the vertex, I have to move 5 units up. Then I'll find the vertex which is on top. And I have to go 5 units down, and I'll find the vertex which is down. How do I do that? Well, from here, 5 units will mean I have to go all the way up to there. And since I am already at 3, after going 5 units up, this will have to be at 8. So that the gap between the center and that point is 5. Next, I have to go 5 units down. Since I am at 3, first I have to cover the 3, taking me back to the x-axis, and 2 more taking me to where that vertex is. So this brings me here, and you have to see that the reading here on the y-axis will have to be -2. So in this case, notice that the vertices, I can't use that plus, minus, and so on. Can I? No. Can I? No. So the vertex, in this case, the vertex will be given as the one on top is they are all at -2 in the x-axis here. So it will be -2, 8. That's the first one. The other one is also at -2, but it's what? This is -2. So these become where the vertices are. But how about the foci? Well, for the foci, we know to say we still have that relationship. B squared is equals to A squared minus C squared, which led us to C squared is equals to B squared minus B. That's A squared minus B squared. Our A, we saw our A was 5 squared, and our B, according to our expression, our B was 3 squared. So this is going to be 25 minus 9, which is equals to 16. So that our C comes out as 4. What does that mean? It means that to find the focus, we have to move 4 units from the center. So from the center, we move 4 units up. We find the first focus. So since it's 4 units from 3, the reading here has to be 7. And then 4 units down as well. Since we are at 3, the reading here has to be -1. Based on that, it tells us that the focus in this case will be at -2, 7, the one up, -2, -1, the one down. Any questions there? Next up, hyperbola. When it comes to a hyperbola, it's similar to an ellipse, but the difference is that one term is going to be negative. So you have a squared minus y squared, and then this is over b squared is equals to 1. So here we're seeing one term is negative. Okay, someone joining us? One term is negative there, which is like that. Now, it can be something like this, or it can be that the x is the one that has a negative coefficient. But basically, if this is what you have, then it implies that you're dealing with a hyperbola that opens to the left. So this hyperbola has, this opens to the left, and what you're going to have is basically something like an ellipse, but only a piece of it. Something like this. Here, of course, you have that. The focus for this is going to be something like this. Now, a hyperbola is basically just an ellipse, but just 2 pieces of it, if I call it that. Or should I say 2 parabolas put together? So you have that, and then you have another one. Let me just copy this, and then orient it properly. This should do. Copy it. But now just make it face the other side. Okay, so this is what we have. Of course, it has to be better than this. This is not really. Let me try to see if I can do something better. Okay, better. So you have this. Not the best. I do have to work. Okay, so this is what you have for a hyperbola. Now the center of the hyperbola will be somewhere right in the middle, something like that. Now a hyperbola will have the focus as the other conic sections, but you don't really talk about the directrix here. We can, but don't really talk about it that much. Instead, we talk about one, the focus, which will be here and also here. Apart from that, we also talk about the vertex, which is here and also here. But the last thing that we talk about when it comes to a hyperbola is going to be the asymptotes. So asymptotes are going to be, you're going to have one line passing like this, going straight like that. Ideally, it's a line that doesn't touch any of these curves. Okay, something like that, not perfect, my graph's not perfect, but that's okay. So that is one asymptote, but then we're going to have two. So usually when making a sketch of a hyperbola, it's the asymptotes that help you know exactly how you're going to draw these. Okay, this is much better. So it's the asymptotes that help you understand where the hyperbola is going to pass. And I'll demonstrate exactly how we use the asymptotes to create the sketch. So when you're placing down these asymptotes, you must also show the equations of the asymptotes. So this is how we describe a hyperbola. Now notice that when writing this, first I focused on where it is opening. Is it horizontal? Is it vertical? Once I was done with that, the rest was pretty much straightforward. Now, the other thing that you have to keep in mind is that the distances here are being measured from the center of that hyperbola. A here will have to be the distance from that center to the vertex, which is from here to there. This is going to be our A. So we're going to have that distance here, and it's going to be a similar distance to there. That is going to be A. The next thing is going to be our C, which is the distance from the center to the focus. In this case, it becomes the distance from here to that point there. And then it's going to be from here to that point there. So this becomes what we'll be using as our C. Okay, now, how do we find C? Because if you look at the expression, what we have is B there. What's the connection? Well, when we're dealing with an ellipse, we sort of say B squared was equals to A squared minus C squared. In this case, for a hyperbola, it's a little bit different. Why? Because C here is going to obviously be smaller than, it's going to be bigger than A, as you can see from here. A is just this short distance, while C is a little bit more. So to make it all add up, this we're just going to switch up. Of course, everything is factored in when deriving the formulas. I'm sure you guys get how it goes. But in the end, B will actually now be given by C squared minus A squared. But the easiest way to actually remember this relationship in this case is just by taking C to be equals to A squared plus B squared. I found this to be the easiest way to understand or remember the relationship between A, B, and C for a hyperbola. Now, if let's say the hyperbola was opening upwards and downwards, as in wrapping around the y-axis. Now, in that case, how would it look like? Well, in this case, what you'd have to do is that, or what you'd have to understand is that firstly, it will have to go something like this. And then, of course, the other one would have to go. I did draw this one a little bit much better, so let me just use it. So is this okay? Looks fine. And then the other one, basically the same one, but just facing downwards. Something like that. So in this case, this is how the equation for this one look like. Well, it's the same thing, but now the one that is going to be negative is x. Doesn't matter where, okay, so I think it does matter. Let me just, usually what we do is when it looks like this, firstly, you want to understand that our A is going to be from here to there. Our C is going to be from here to the focus, which is basically the same as from here to here. And also the other one, C is going to be from there to there. So C and A are now in terms of the y-axis. And this one now changes. Now, instead, in the previous one, we had x squared over A and y squared over B squared. Now, what we're going to have is we would have to look at x squared over B squared, and then we'd have y squared over A squared is equals to 1. Okay, so this is what would end up with in this case. Okay, so Yeah, basically this is the hyperbola, and just as we saw, this doesn't look too good. So if it opens on the vertical axis, as in the foci is on the y-axis, the center is on the y-axis, and everything else, in this case, just swap them. The first one looks like this, just swap which one is negative. Here we had this, and this being positive. Now just swap them so that now y is the one with the a squared, and then x is the one with the b squared. Then this is equals to 1. Sorry for that. I think I was having a lapse somewhere there. But basically, this is how it goes. So now they have just switched position. In this case, x is the one that comes with the minus, and y squared is the one that comes out positive. But the one that remains squared is still, as in the one that remains with a is going to be the one which is positive there. So this is how it is going to end up in this case. And so this is for this setup, y squared over a squared minus x squared over b squared is equals to 1. Now, if it is not centered at the origin, we know how it goes. It just means that something is being added or subtracted to y, something is being added or subtracted to x. Now, the last thing is, how do you find the asymptotes? If you wanted to find the asymptotes, either case that you're looking at, just change this. Instead of having a 1 there, place a 0 and solve the equation that you have. Simplify it, make y the subject of the formula. What you're going to end up with is going to be an equation of a straight line, which is going to be the equation of the asymptote. Okay, now with that in mind, let's look at some examples. But before we go to the examples, any questions? Okay, looks like we're okay there. Consider this simple example. So we have y squared over 4 minus 5 squared minus not 5, x squared over 5 is equals to 1. So we want to find the foci, the vertices, and the asymptote of the hyperbola. And maybe throw in a sketch there. So let's find what we have here. Firstly, we know a comes with the term that is positive. So here a squared is equals to 4, so that a is equals to 2. B squared is equals to 5, so that b is equals to root 5, I mean. How about c? We know to say for a hyperbola, c squared is equals to a squared plus b squared. This implies that when we add them, a squared is 4, b squared is 5, so we get 9, and then square root, c comes out as 3. So you now have a, b, and c. So finding the foci, the vertices, becomes easy. This is a hyperbola centered at the origin. And when we look at where the negative is, it's with the x-axis. So you know this wraps around the y-axis. So to give you a picture, before I even label what they are, we use an image and start to sketch our hyperbola. So our y-axis is here, our x-axis is this side. So to sketch the hyperbola, the first thing that you need, if you're doing it formally, of course, in proper way, you have to first start with the asymptotes. But of course, in most cases, as a student, you want to do this very quickly, very roughly, and then the asymptotes end up being the last thing that you do. I can still show you that. But if you're going to do it the standard way, then asymptotes must come first. And to find asymptotes, you must first get this and plug in 0 where you have 1 and make y subject. So you have this. Putting 0 where we have 1, we end up with this equals to 0. Make y subject, we end up with this equals to x squared plus 5. So that in the end, we have y squared is equals to 4 over 5x squared. Square root both sides, we end up with y is equals to plus or minus root 4 over 5x squared. Simplify this, you get two equations. Y is equals to positive root 4 over 5x, and the other being y is equals to negative root 4 over 5x. So these become the equations of the two asymptotes. Ideally, you want to start with these, but and then move on from there. But generally, how it goes, it's like this. Most cases, the easiest way that I use to sketch is first start with A, the vertices. A is at 2 units from the center. This is centered at the origin, and it's along the vertical axis. 2 units, let's say my 2 units comes here. So meaning the first one will have to open upwards from here. Done. It's a sketch. No one will crucify you for not being perfect. So that is the first one. The second one, we know to say it has to be 2 units down the other side. So we know if this is at 2, then this has to be at -2. So bring it here. Just rotate this. Done. Next thing, the focus. The focus, according to what we did, the focus is at 3 units up and 3 units down. So if this is 2, my 3 can be approximated to be there. The other one, 3 can be approximated to be here, so -3. So done. Next up, we have the asymptotes. Let's plug them in. We have two asymptotes. One has a positive gradient, will come down like this. The other one has, of course, you want to make sure this passes through the origin. Does this do it? Almost. Does this do it? Yes, it does. And then let's just copy this. And let's just do that. Okay. So we're done with our asymptotes. So what you just want to do is you want to label the asymptotes. So the one with the positive gradient will go up, which is this one. And then the one with the negative gradient will be this one, the one slanting downwards. So we have sketched the equation, but I just want to state the ones they wanted. Since they wanted the vertices, so for the vertices, we have 2 of them. So I'll just use plus or minus 2, 0. Here it works. The foci, since again, this is the origin, so I have plus and -3, 0. That works. So that has been sorted out. Everything has been indicated. Okay, so any questions there?
Question.
Go ahead.
Your major vertices as 2, not root 5.
Let's see. Root 5 was what? Root 5 was B. What are you saying? I'm taking it as 2, not root 5.
But we take the major vertices as the larger number.
No, we used that for the ellipse. For this one, we moved away from that. I think I specified you only do this for an ellipse.
Oh, all right.
Yeah.
So you always take the one that is the first?
The one that is not negative.
Okay, okay.
Yeah. Like in this case, if you recall here, when y was negative, the major or the principal axis was along the x-axis, the positive term. You've seen that?
All right, okay. Yes.
Okay, so basically this is how it goes. Okay, now, ideally, these conic sections, in as much as we've seen their standard expression, so we've gone through everything now. In as much as we've seen their standard expressions, their general expression or their general standard, regardless of what you're looking at, will always be a two-dimensional quadratic equation where you have ax squared, then you have bx, but this one is going to be the cross product with bx and y, and then you have cy squared, and then you have dx plus ey, and then you have plus f is equals to 0, which is generally going to be the standard expression. But for now, we are focusing on conics which do not have the cross product, where you only have this. So we're going to take something like this. So this is what you're going to have. Of course, this is just some general representation. Now, you should be capable of transforming something given to you in this form and change it so that it gets to match either one of the conic sections we have described. So you should be capable of doing that. Once you make it match, then you can easily sketch or figure out whatever they want you to figure out. So you should be able to do that. A good example is this question. It's coming from, this is 2017. I think this is a test or a quiz paper, I'm not sure. But in this case, look at what they gave. They gave something like this. I'll label this as example. I don't even know where I am, so I just say example 2. But I'm sure it should be example like 6 or 7. So you have something like 9x squared plus 16y squared. Then you have minus 96y minus 72x. Then this is equals to minus 144. So you have no clue what type of section this is. How do we work with it? Well, you have to complete the square. 9x squared plus 16y squared minus 96. That's 16 or 96. That's 96y. Then minus 72x plus 144. The goal about, or the rule about completing the square, first you don't have the cross product. Nice. So group everything with an x, everything with a y. Basically similar to what we did when we worked out that 3D problem sphere. Then you have 16y squared, then you have plus, no, minus 96y. I've grouped everything according to how similar they are. Once we are here, now complete the square for each term. So that is what you'd have to do. And remember what I mentioned when we were doing that sphere. Before you complete the square, you want to make sure that the coefficient of the squared term must be 1. So let's do the x part first. If I just focus on the x part, let me go blue for it. So pull out 9 first, so that you are only dealing with x squared being positive. So if I pull out 9 from 72, how many times does 9 go into 72? Is it 8 times? 8. Then from here, we can complete our square. X squared minus 8x, you know how it goes, half this, add it, half it. It's minus 8, so half of minus 8 is minus 4. Square it, add it, then subtract it. Again, I'm just focusing on this part. Then next, this term and this term, x minus 4. Then this is minus here. Then the 4 squared is 16. Distribute the 9. You now have 9. Then you have 16 by 9. What is 16 by 9? 144. So all this is just the first term. We have completed the square. Now I have to do the same thing for the second term. For the second term, we have 16y squared and 96y. Is that the one? Yes, 16y squared minus 96y. Again, I want to ensure that y squared remains with the coefficient 1. So what is 16 into 96? 6. Then, like we did earlier, y squared minus 6y, half of minus 6. Don't forget that minus. So it's minus 6 minus half of 6, which is minus 3. And then this has to be squared. We've added it. Now we just subtract it. Then we get y here, and we get minus 3 from those brackets. And then we get that minus 3, we'll square it. So we get 9. Distribute the 16. There's a square here. What is 9 minus 16?
7.
What's that?
9 minus 16 is 7.
No, 9 by 16. We are multiplying.
That's 144.
144. Same, did you not do the same application earlier? Oh yeah, it was 9 by 16 again. Nice, 16 by 9. So we have now completed the square for the two parts. Let's put them together. Okay, so this is the first one. And this is the second one. So don't forget, the other part, it had two parts. There was this, then there was this. The last part was that 144 is equals to 0. So this is, here we have plus 144 is equals to 0. So how do we complete this? We see the 144 and this can easily subtract out. The 144 that remains goes to the right. Plus 16y minus 3 squared is equals to 144. Now this is starting to take shape, but we still see the coefficients there. And we know in this case, because these coefficients are not the same, we know this is not a circle. So divide everything by 144 so that the right side is a 1. So over 144. So we now have 9 into 144. Of course, that will be 16. So this is x minus 4 squared over 16 plus y minus 3 squared. This will be 9 is equals to 1. So look at this expression. Can you tell me what it is? Can you describe it? State what, okay, to describe it, I'll just say state the center, give me A, give me B. Give me A and B. State the center and A and B.
The center is at 4,3. Then A is the square root of B is the square root of 9.
Yeah. Which is 3. Notice that this implies that C is 5. So notice that having done this, it means that we can easily get what the center is. The center is found already. You can get what the focus is. We can get what the vertices are. And what conic section is this? ellipse. Yes, this is an ellipse. Okay, so basically that is what you had to do there. Okay, so we still have more things to look at. We have rotation of axis, we have eccentricity, directrix, discriminant test, and the likes. Perhaps let's still have a few minutes. Let's do at least one of those before it's 22. Okay, this was long. Okay. Now I did want us to look at cross product as well.